Okay, in this video we are going to get the matrix ring decomposition of a ring that is semi-simple as a module over itself. And before we do that, let's remember the vector space analog of this situation. First of all, if just take an n-dimensional vector space V over a field F, and notice that the ring of linear transformations on V is isomorphic to the n by n matrices, the ring of n by n matrices over F. And this happens via an obvious identification of a linear transformation with an n by n matrix with respect to a basis, or two if you want the codomain basis to be different. But you see, this we already did. I mean, we've shown how this is done and why this is done so in our second video about purity. So the viewers may refer to that video to see how this is done in a very simple way. Now, before we move on with the semi-simple ring case, let's actually generalize it as a nice exercise. If a module is isomorphic to the direct sum of n copies of another module A, then the ring of endomorphisms of M, which of course is a ring under pointwise addition of functions and as its addition, and function composition as its multiplication. Then we have this. As I said, we are no strangers to this result because we already know its assertion in the case of a ring and in the case of a field. Let's remember it. Now, what I've just said are actually two special cases of this fact that we stated above. For example, when you take A to be the ring itself as a module over R, again itself, then the endomorphism ring of M is simply the ring of n by n matrices over R. But we are saying n by n matrices over the endomorphism ring of R. So is there a discrepancy? No, because the ring of endomorphisms of R as a module over itself is simply isomorphic to R. We have and M isomorphic to M and R. So the ring of matrices, n by n matrices over R. In the field case, when R is a field, then we are talking about we recover the well-known result in linear algebra, namely the one that says the ring of linear transformations on an n-dimensional vector space V over F, over the field F, is simply isomorphic to the ring of n by n matrices over F. So it would be nice if the viewer attempted to get the even more general form of this result, where the module A here is replaced by various modules for each copy of n. Like, for example, when M is a direct sum of different modules, not necessarily isomorphic modules, M1, M2, and so on up to Mn. Okay, now we can begin our sketch of the proof that I mentioned, I alluded to earlier. Take a module M, take a semi-simple module M. Then assume that M is the direct sum, a direct sum of simples Si, and assume furthermore that S is any simple submodule of M. And what happens is that this simple module S is isomorphic to one of the Si written above. How this happens is simple, because one of the projections, canonical projections from the direct sum of Si's onto the individual Sj's, when restricted to our module S, must be non-zero. It is this one I'm talking about. Once it's non-zero, then by the simplicity of S, it must be, and Si, it must be an isomorphism. Okay. Next, we define the homogeneous component of a semisimple module. So once again, we are assuming M is semisimple, and take any simple module S. It doesn't even have to be a submodule of M, or isomorphic to one of them. Then we will define Hs to be the sum of all simple submodules of M isomorphic to S. We call this the homogeneous component of M with respect to S. One thing is clear, namely that M is a sum of its homogeneous components, where S ranges over any simple modules that you can think of. If S doesn't have a copy inside M, then Hs will simply be 0. So this sum is meaningful. In fact, because of what we just said in the previous slide, this is a direct sum. Since we are interested in the semisimplicity of the module R, the ring namely, we will now switch to the consideration of a finitely generated semisimple module, in which case there are finitely many non-zero homogeneous components. So if M is finitely generated, then M is a direct sum of its homogeneous components. And clearly, there are no non-zero homomorphisms between two distinct homogeneous components, simply because the homogeneous components are semisimple modules, and their factors are also homogeneous with respect to the same simple module. So for example, H is a sum of simples all isomorphic to, say, S, then so is every factor of H. From this it follows that the Hom group from Hi to Hj is 0. Okay. So what happens if that is the case? What happens if these Hom groups are 0 once the indices are different? Well, in terms of the endomorphism ring, things become a little easier. So the endomorphism ring of M will be ring isomorphic to the direct product of the rings of endomorphisms of Hi's. Once again, this could be seen as a special case of what we discussed in the previous slides about the endomorphism ring of a direct sum. And using the fact that Hom Hi Hj is 0 when I is different from j, we can easily see this. So I leave it to the viewer to fill in the details. So what happens, for example, when M is our ring R in the above situation? What happens is, well, two things. This fact implies, and let's mark it with an asterisk, if I can do so. 1, for distinct pairs of indices j and I, hj times hi is equal to 0. That's the first thing that happens. It's easy to see this because hj, hi could be viewed as sums of the images of some homomorphisms from hi into itself, realized by left multiplication by elements of hj. The details are again quite easy, straightforward, so I leave it to the viewer. And that's the first thing that's implied. And then, so another thing that can be noticed by this equality is the fact that hi are actually ideals, so that hi are ideals. And the second thing that happens is, the second thing of interest to us, of course, is the fact that R, which we know to be isomorphic to the ring above endomorphisms of itself as a right module, which now is isomorphic to the direct product of the rings of endomorphisms of the homogeneous components. Now we may be viewing these things initially as R linear maps, but it will be easy to see that HIs being ideals, they are rings whose identities are the respective central idempotents generating them, and there are submodules and HI submodules, namely submodules when they're considered as modules over R, or submodules when they're considered as modules over themselves as rings, are the same, and so are their endomorphisms. Then we have this. We no longer have to view the HI as modules over R, but we will simply refer to them as rings, modules over themselves. Now each HI is isomorphic as a module to a finite direct sum of copies of a simple module, say I. But then what happens is, then the endomorphism ring of HI, which of course is the same thing, or is isomorphic to HI itself, but we want to see it as an endomorphism ring of something so that we can pass to the matrix ring. So being a direct sum of ni copies of the matrix ring, the module Si, its endomorphism ring, by a result we proved earlier, is isomorphic to the ni by ni, the ring of ni by ni square matrices over the endomorphism ring of the simple module Si. And that that is a division ring. Each simple module's endomorphism ring is a division, and call that division ring Di. So now we now have one more component of the Wedder-Bernard in general form, namely that R is the semisimple ring R is isomorphic to such a matrix ring. The product of matrix rings over division rings. But then notice that this has happened when R is only as semisimple as a right module. On the other hand, what we get on the right side of the isomorphy seems to be symmetric. Left-right symmetric, right? We could have obviously carried out the same argument with R as a left module and still have gotten the same thing. Which gives us as a corollary, I should have said, which will give us, after a little more work, as a corollary that left and right semisimplicity are the same thing. So there's there's no need to distinguish between them. But now we need to do a little more. See, this situation arose as a necessary condition of the assumption that R is a semi-simple right module. Now let's prove, conversely, that any ring of this form is semi-simple as a right and as a left module. I think a sketch will be sufficient here again. Now, conversely, assuming the converse that R is a direct product of such rings, such matrix rings, where Di are division rings now, all we have to do is to observe this. First of all, each matrix ring in this product is a simple ring, which means the only ideals, two-sided ideals, are 0 and the ring itself. And this is because the ideals of a matrix ring are known to be matrices over an ideal of the ring. This is known to be no longer true for right or left ideals, which also is a good exercise to prove. But this is enough to say M and I, Di are simple rings. And they are furthermore semi-simple ring, right and left. Well, how do we get the semi-simplicity right and left of this matrix ring? First of all, rows of it are simple right ideals. And similarly, columns are simple left ideals. So each of these matrix rings is a sum of its, can be viewed as a sum of its rows or as a sum of its columns, and that would give us these matrix rings are semi-simple as right and left modules. Hence the symmetry follows. So we obtain that R is left as well as right semi-simple if it's a direct product of matrix rings of that form. But then this implies that a right semi-simple ring is left semi-simple too. So it gets us this. Combining everything that we have done so far in the last 3-4 videos, in the last, I guess it's 3 or 4, whatever, this is the 4th one. So in the end we have the following equivalences, which characterizes a semi-simple ring. So any ring of this kind is called a Wedeber ring, and right and left semi-simplicity are left-right symmetric. Here we mean by J the Jacobson radical. Jacobson. Okay, maybe I should write it so. Now in the next video I'm going to try to give you a little flavor of what kind of extensions of this theory are possible. So see you in the next video. Thank you.